That's small. Nice. So a linear function, right, is any function of the form y equals mx plus b. We call them linear functions for the good reason that their graphs are lines. So as we checked last time, those are both linear functions. Graphs are in fact lines. This function, y equals x squared plus 1, its graph is not a line, it's not a linear function. So the thing that we're going to try to build in the next 15 to 20 minutes is the study of the idea of what information do you need to determine a linear function, to figure out an equation. And the idea is you should need like two facts. A linear function is specified by f of x so a linear function is specified by those two constants. So if you know two facts, that should be enough to determine that linear function. And so maybe we'll start with one thing you can extract from a line, and that's its slope. So given any line, the slope of that line, let's draw a picture. Let's take 2 points, x1, x2, x1, y1 rather, x2, y2. You can draw a line given 2 points on it. You can also compute the slope, right? The slope is like the rise over the run of that line. So if x1 and y1 are 2 points on a line, then the slope of that line is given by rise over run. If you prefer to write it as delta y over delta x, oftentimes in mathematics or in physics, the symbol delta is used as a shorthand for how much does this thing change. And well, now let's just write it down. It's how much y changes, so I guess that's y2 minus y1 over x2 minus x1. There's how to compute the slope of a line. So let's see this in practice. Let's consider this line, y equals 2x minus 4. Let's try to compute the slope. So that requires us to find 2 points on the line. And there's some instructions for finding some points on the line. But on the other hand, like just looking at that formula, what do you think the slope ought to be? 2, probably. So here's some fancy takeaway that we'll get on the next page. Slope of the line given by y equals mx plus b is m, but let's see that in practice happening. So let's try to find the slope using these 2 points. So let's see, when x equals 0, let's compute the y value you get. You get a y value of 2 times 0 minus 4. Looks like it's minus 4. So 0 minus 4 is a point on the graph. When x equals 1, what y value do you get? Here a negative 2, but you plug in that x value, you see what you get. Two times 1 minus 4. Yeah, that sure looks like it's minus 2. So I now have 2 points on the line. Let's compute the slope. Change y value minus x value over corresponding x value minus corresponding x value. All right, you take that, you simplify that out. I see in the top negative 4 minus minus 2. Yeah, does that simplify down to 2 eventually? Yeah, awesome. Seems to work out. So there's the general fact that's worth building to. The slope of the line given by y equals mx plus b is that parameter. So let's hit here's the next sub-goal. Any two facts should be enough to specify a line, but in particular, if I pick 2 points, there should be only one straight line between them. So I should be able to find an equation for the straight line between those 2 points. Let's do exactly that. Suppose you are asked to find an equation for the line between 1, 3, and 3, 2. So that is, get something in the form y equals mx plus b that passes through those 2 points. And given the information that's already given, what's the first thing that you would want to do? Yeah. Find the slope. Well, that would tell you what the m is. And I know 2 points, so I can find the slope using them. So let's see, the slope, which is the m, is the change in y divided by the change in x. Change in y divided by the change in x. People with me so far? And maybe we'll even like draw a picture. All right, so that tells me the slope is negative, so it should be going down, but the slope isn't too big, so it should be reasonably flat. We can check those intuitive things by looking at a picture. 1, 3, 3, 2. Yeah, looking at that slope, as x goes left to right, it seems to go down. Slope is negative, but the slope isn't terribly big, so -1/2 seems reasonable. All right, so we know what the parameter m is. That's good. Let's try to figure out the parameter b. And maybe I'll give the following idea. If you know the slope of a line and a point on the line, you can write that line in what's called point-slope form. So the point-slope form of a line is that that line is given by y minus a y value on the line is equal to the slope times x minus some x value that you know is on the line. So in this case, are you given a single point that's on the line? Yeah, you're actually given 2 points. So let's just pick one and use it and see what happens. How many people would rather use 130? How many people would want to use 32? All right, those of you who want to use 130, use it. I'll use 32, and we'll see how our final answers compare. So apparently then, y minus the initial y value should be equal to the slope times x minus the initial x value. And on the one hand, that could be a final answer. It is an equation that gives the line. But do I have that in the form y equals mx plus b just yet? Now let's do some, I guess, simplifying and work on what that should be. Add 2 to everything in sight. Do some distribution. And now I guess I see, on the one hand, this is y equals mx plus b. It's y equals -1/2 x plus 3 halves plus 2. How would you simplify 3 halves plus 2? Or just what does it simplify to? 3.5? Yeah, that works. 3 halves is 1 and 1/2. 1 and 1/2 and 2 more. Yeah, that's 3 halves. Excuse me. So this line is given by y equals -1/2 x plus 3.5. Nice. People feel pretty okay? So I don't think I will here, just in the interest of time. But let's suppose this was like a homework problem and you wanted to check if it was correct. What are some things you could do to check if this is good? Yeah.
Try the points that you use.
Yeah, this is specifically supposed to go between these 2 points. So you better be able to plug in each of those x values and get the resulting y value. That's a good check to make. What are some other things you could do to check? Well, at home you'll have like access to computers and graphing calculators and stuff, right? Yeah.
But if you have like a scientific calculator, like a TI-84, you can just plug it into like the equation, see if it works with the graph.
Yeah, you could electronically graph it, see if it goes through the points. You don't even need a TI or anything. I've looked a few times over to this thing called Desmos. Like, there's no need for you to own a graphing calculator. Everything that it does, you can find free tools that do better online anyway. But yeah, any tool you would like to use to graph, you can look at an electronic graph. So in general, if you're given 2 points on a line, some steps to follow that will give you the graph. Or first, compute the slope. Put the thing in point slope form. And finally, solve for y and then do some simplifying to get it into the form y equals mx plus b. Fair enough? Any questions right now? Hopefully this also feels fairly reviewy. Good. So the next thing that I want to hit is the idea of intercepts given an equation for a line. So, intercepts, what are they? What is the x-intercept of a graph? Yeah.
Y is 0.
Yeah, so there are going to be 2 lines. The point, or points, on the graph with y equals 0. What's the other way of saying that same concept? The points with the graph, it's the x-axis, I guess? It's the same thing, so maybe I won't even bother anyway. Similarly, what's the y-intercept of a graph? Yeah. So, let's combine those two. Oh, I'm not on the... You guys let me get away with that for quite a while. So, let's find the x and y intercepts of this thing. What should we do first, x-intercept or y-intercept? X-intercept? Y-intercept first. 0 preference. All right, I'll do them in order. I guess x is written first here. So you find the x-intercept as the points where y equals 0. Well, I have an equation of the thing, so let's set y equals 0. 0 equals 3x plus 4. Does that look like you could solve that for x? Yeah. Do it. What's x? Cool. Anyone want me to do that in any more detail than no detail whatsoever? Cool. So, let's suppose I ask this question, and they submit an answer where the x-intercept is at negative 4 over 30. Is there anything wrong with that as an answer? Yeah.
It's just x value, it's not the intercept.
Yeah, the intercept itself is a point. It's not just a number. So this is a pedantic difference, but it is a difference. So let's write down the answer. There is an x-intercept at the point negative 4 over 30 by 0. Everyone happy enough? What about the y-intercept?
Yeah. Maybe y-intercept be 0 and positive 4?
0 and positive 4. Indeed it would. Right, so what do? On the one hand, you could plug in x equals 0. Oh, but then everything just simplifies down to just y equals 4. Great, yeah, that'll do. In fact, there's one handy takeaway here. There's a general effect. The y-intercept of the line y equals mx plus b is b. So the slope is given by that m. That b gives you the y-intercept. That seems reasonable too, right? Like that's not even a fact worth remembering. That's just like, how do you find the y-intercept? You plug in x equals 0, all that's left is b. Groovy. Yeah.
If it says like y equals 3x minus 4, the y-intercept is like negative 4 then?
Yeah. Absolutely. Yo. I didn't remember the slope that you told me, but it didn't matter anyway. Cool. All right, so let's combine this again with this idea that if you have two facts about a line, that's enough to tell you what the line is. So let's hit this bullet point. So let's suppose that you have a line. You know its y-intercept is at 0, 3. Its x-intercept is at 3, 0. Those are two facts about a line. That should be enough to determine the line. How would you want to determine this line? Yeah.
We need to find the slope first.
Finding the slope seems like a good thing to do. Let's find the slope. So the slope, right, that would be the m if we have this in the form y equals mx plus b. It's given by the change in the y-coordinate divided by the change in the x-coordinate. And I feel like if I just stall long enough, someone will tell me what the slope is.
1.
I hear a 1, but it's not 1. I think it's -1. So let's just do that check real quick. And this is maybe worth highlighting because I also know exactly what mistake you made if you told me the answer was +1. So the slope is the change in the y values. So this y value minus that y value divided by this x value minus this x value. Yeah, that's going to be 3 over -3, that's negative. So if you compute the slope, but you screw up the order and you have the y-coordinates in one order on top, you have the x-coordinates in the opposite order on the bottom, they'll be off by exactly a negative sign. And you know what, that's a good reason to draw a picture because a picture, even if it's pretty imprecise, will tell you that you're... So let's draw the line. Its y-intercept is 0, 3. So this line has to go through 0, 3. It has to go through 3, 0. So it's that line. By drawing that line, would you say that slope is positive or negative? Negative. So it better be negative, whatever it is. So that's just, it's a good checksum to have. You can draw a picture and figure out if your answer is reasonable. All right, so we know the slope. That's m. I guess we still need to find b. How could we find b? Say that out.
They gave it to you?
Sorry.
They gave it to you? Is it in y-intercept?
Yeah. There's this fact that b is always the y-intercept. B equals the y-coordinate of y-intercept. So that's 3, I guess. All right, so this is given by y equals mx plus b. Let's fill in m and b. What's m? -1. What's b? This line is given by y equals -x plus 3. That feel pretty okay? So the last two things that I want to hit are the notions of parallel and perpendicular lines. And so what is a parallel line? Well, two parallel lines are two lines that never cross each other, something like that. What can you tell me about the slopes of those two lines? How do they look like they compare? Yeah.
Well, if it's a parallel, doesn't that mean like look, the slopes are the same?
Yeah. Yeah. Two lines are parallel if their slopes are equal. In terms of formulas, two lines y equals mx plus b and nx plus d are parallel if their slopes are the same. So it's just m equals n. So if you're asked to say, find the line through a point parallel to this other line, well, this gives you two facts. So let's try to unpack this just a little bit. Maybe we won't do it at all of it. If a line is parallel to this line, what can you tell me about the slope of this new line we're looking for? Yeah, it's the same. It's the same. So this new line has slope 3/2. Oh, cool, but that tells you what, like, the m should be. So if you know that the slope is exactly 3/2, and you know it goes to the point 1, 1, is that enough information to determine the line? Yeah, I guess, like, we've done this already. Put it in point-slope form, and then solve for y and simplify until you write it in form y equals mx plus b. People want that example discussed in any more detail? Well, I'm actually finished. All right, cool. So, last concept that I want to hit is the idea of perpendicular lines. So two lines are perpendicular if they meet at a right angle. And here, just for visualization's sake, are two lines. Y equals 3/2 x plus 4, y equals negative 2/3 x plus 2. Do those two lines look like they meet at a right angle? Yeah, great. Do their slopes look like they have anything to do with each other? Yeah.
The slopes are reciprocal as the first one's 3/2 and the other one's negative. That's 2/3.
Yeah, so you left out A1 when you said they were reciprocals of each other, but then you put it back. So negative reciprocals of each other. Reciprocal just means you flip the fraction. You also get negative sign. And there's a general effect. Two lines in the plane are perpendicular if their slopes are negative reciprocals of each other. So let's state that fact. Two lines, y equals mx plus b and y equals nx plus c, are perpendicular if the slope of one of them is negative 1 over the slope of the other. Oh, sorry, that was off screen. All right, so let's just check. Are those two lines actually perpendicular by that rule? Yeah, and maybe this is just a good chance to remember how fractions work. So let's compute negative 1 over 3/2. What does it mean to divide by a fraction? Yeah, multiply by the reciprocal, meaning the fraction that's that same fraction but upside down. Yeah, cool. That works out. Groovy. People feel pretty okay? So there's one last example in here, but I kind of want to get to the content, so I'll see what what was allegedly supposed to be today's content. So I'm falling behind. That's okay. Find an equation for the line through 1, 1, perpendicular to y equals 3/2 x plus 4. So, show of hands, how many people think it's worth going through that one last example? Okay, awesome, let's do it. So, let's suppose you want to find an equation for a line through this point, perpendicular to that line. Well, it's perpendicular to this line, so I know how to compute the slope of the new line, right? it should be negative the reciprocal of this slope. So the new slope, this thing that gets called m, will be negative 1 over 3 over 2. Yeah, negative 2 thirds. All right, so we find the slope of this new line. Are we given a point on that line? I hope so. Let's use that. Let's put this in point slope form. So it's y minus the initial y coordinate, so y minus y0 is equal to slope, negative 2 thirds, x minus initial x coordinate. Yeah.
If we skip the calculation for the slope, would you break it as well?
Yeah. So the only reason that this is a better thing to remember than the law of reciprocal is maybe instead I tell you that the slope is like 3.57. I don't know what the reciprocal of that should mean, but I know what negative 1 over 3.57 should mean. But yeah, if you just said, well, I know it's going to be negative the reciprocal. Great. Yeah. Yeah.
Do we have to do point slope, or we just did like y equals mx plus b and just found b?
Oh yeah, let's actually do that. Let's do it that way. So I know this thing should be in the form y equals mx plus b. And I don't know what b is yet. But what xy coordinate do I know is on the line? 1, 1. So I should be able to plug in y equals 1, x equals 1, and solve for b. That look like something that's easy enough to solve for b? Yeah, I hope so. Multiplying by 1 doesn't do anything. Add 2 thirds to the other side. 1 is 3 thirds plus 2 thirds is not a very good 2, is b. So it looks like 5 over 3 is equal to b. Yeah. It's good to have 2 different ways to do things, yeah.
So like for the test, will you ever like say it's like use point slope form for this specific problem, or use specifically y equals mn plus b for this specific problem?
I might specify what I want the final answer to look like. If I say I want you to give me an equation for the line as a function, then I want y equals something.
Okay.
And I want it maximally simplified, so I guess it'll have to be y equals mx plus b.
Okay.
If I say perhaps which of the following gives an equation for this line, you better be able to recognize point slope form then. So it's worth knowing both of them.
Okay.
Yeah, I try to avoid being pedantic in terms of use exactly this technique.
Okay.
But, you know, there will be times when I will demand it.
Okay.
Cool. Any questions so far? Nice. Oh, yeah.
Oh, no, man.
We're happy?
I figured it out.
Okay. I'm glad I could help. So the last thing I want to hit on is some stuff just about general abstract graphs and graphs as they relate to functions. So let's begin with this very example. So here is the graph of y equals the square root of x, the graph of the square root function. So tell me, by looking at that graph, is 4, 2 on that graph? Yeah, it is. You locate the point 4, 2, I guess it's there. 4, 2. Should that point be on the graph? It's better if it is. Why should it be? Yeah.
Because if that graph represents y equals the square root of x, you just plug 4 into the square root of 4 would be 2.
Yeah, right. There's an x value. The square root of that x value is 2. So yeah, that point 4, 2 should be on the graph. Is there any point on that graph with x equals -1? No. Should there be? Why not? Yeah, you're not allowed to put any negative under a square root if there was such a point. The y value would have to be the square root of -1, which, well, at least for us anyway, well, let's say is not real. Cool. In general, if you have the graph of a function, you can always understand the function by thinking backwards from here. If you have the graph of a function, you can use it to compute. If you want to get f of x, nice. And this is building up to something. There are a few things which, for the most part, I assume you've already heard, things like the vertical line test. So if you have some function you want to understand, and you have a graph of a function you want to understand how to evaluate, you can use the graph to do so. So here is something that I will argue is the graph of a function. If that is the graph of a function, tell me, what is f of 1? Well, let's do that. Let's take this x value of 1. What y values do I see on that graph with that x value? 1 and -1. So according to the instructions above, it sure looks like f of 1 should be 1 and -1. Is that allowed? No. Function has to send a single input to a single output. F of 1 cannot be two different things. This is not a function. And this thing, thinking about vertical lines, tells you it's not a function. The vertical line test says that if you draw some graph in the xy plane, that graph is the graph of a function if the graph crosses every vertical line at most, oh no, that's annoying. Should hold up. Okay. The graph crosses every vertical line in at most one point. Because that was the problem here. This was not the graph of the function because that vertical line crossed the graph twice. So let's use that test. By using the vertical line test, tell me, is this the graph of the function? No. Why not?
Let's get at 2 points.
Yeah. There is at least one vertical line which hits the graph at least twice. Is the second graph the graph of a function? Yeah. Draw any vertical line you want? Yeah. It hits the graph exactly once it looks like. That final thing, is that the graph of a function? Yeah. Right, you draw some vertical lines. Yeah, these ones cross in exactly 1 point. That vertical line crosses the graph in 0 points, but 0 is at most 1, so that's acceptable. So the things you know about functions can be computed from graphs. We've seen that whether or not a thing is a function can be determined from a graph. Let's try to describe how the domain can be determined from a graph by thinking about a single example. Let's skip out. I think g is the more interesting function. So this function, y equals g of x. Is that the graph of a function? Does it pass the vertical line test? Yeah, cool. That's good. So does f, but I'm going to care about g only for time's sake. by looking at the graph of y equals g of x, so I'm going to do that one, I'm going to skip 2. So tell me, by looking at that graph, what is g of 0? So I see like heads shaking. It's not. So maybe the efficient way to write that is g of 0 does not exist. What about g of negative 1? G of negative 1 is?
Negative 1.
Aha! So this is exactly a trap set. The open circle on the graph is intended to tell you that that point isn't actually on the graph. It gets really, really close to that point, but it never quite makes it. So that point, negative 1, is not on the graph. So in truth, g of negative 1 does not exist. Similarly, a closed circle will mean it is on the graph. So tell me, what is g of 1? Negative 1. A solid dot means the point is on the graph. G of negative 2. I think I heard some 2s. I think it's almost pretty close to 2. All right, whenever you're reading things off from a graph, things might be a little bit approximate. No, not negative 2. What's g of negative 2 close to? That seems more reasonable. Okay. I was hearing things, but I don't know what I was hearing, and I just believed the voices. Which I assumed were your voices, but might not have been. Could you use this information to determine you could use this information to determine the value of g over any x, what g of x is. And importantly, you could even determine whether or not g of x even exists. So let's try to compute the domain. And maybe I'll zoom in some and play some with the zooming in. So these y values out here, x values. Do you see any y values over these x values? So are these x values in the domain? No, I see no y value over. I don't know how to evaluate g at negative 4. But once I get to negative 3, is negative 3 in the domain? Yeah, you can tell me what g of negative 3 is. G of negative 2 is in the domain. Is g of negative 1 in the domain? No, sorry, it's negative 1 in the domain of g. It's not. What about numbers a little bit bigger than negative 1? Are these x values in the domain? No. And then 1 and changes again. So what is the domain of this function? Negative 3 to negative 1. Someone was saying, and it was good. I don't know who, though. Cool. Okay, let's get the brackets and parentheses right on. Oh, Christ. Yeah, thank you. What about the brackets and parentheses there? Groovy. So, whenever you see any function, you can compute the domain of it. Whenever you see a graph, you can compute the domain of the underlying function. It's just all of the x values you see on the graph. That makes sense? Yeah.
In the domain, you don't include y. Well, that's the range, isn't it?
That's the range. Excellent. So this is a fantastic segue. Given the graph of a function, the range of that function is all of the y values you see on the graph. And let's just see if we believe that. So by looking at this function. Let's try to determine if 2 is in the range. Remember, 2 being in the range means that some input goes to 2. By looking at that graph, is there an input that that function sends to 2? What input does it? Say that all. 3-ish does it. Let's just see that. There's an x value of 3. Yeah, it looks like you get to a y value of about 2. So what input x gives you f of x equals 2? It looks like x about 3 results in f of x equals 2. Cool, so some input gives you an output value of 2. So 2 is in the range. I think my handwriting is degenerating a little bit. Yeah.
What does it say before the about 3? Is that an X or a Y?
It's an x. Yeah. Yeah. X about 3 results in f of x equal to 2. In particular, something gives you an output value of 2. Is there an input which results in an output value of -1? No, it looks like all the output values are positive or 0. -1 is not in the range. And all this agrees, right? There's a y value of -1. This graph never achieves that y value. So -1 is not in the range. People feel pretty okay? Any standing questions right now? All right. 5 minutes. I think that's enough time to get through this, and then I'll give the idea of what is missing. So let's hit, I don't know, for efficiency's sake, let's discuss these first 2 examples. So that first example, maybe I'll, in order to make some things clearer anyway, put some arrows decorating these. Can you determine the domain and range of that function using the stuff we've talked about so far today, without knowing what the formula for that function is? I think so. What is the domain of that function? Yeah.
-50 to -1, and then 1 to including -1 and 1.
Oh, maybe I'll ask a silly question. Do you include or exclude infinity? You exclude. You always exclude infinity. Yeah, the domain is all of the x values that you see on the graph. I see x values that are extremely negative. Oh, but then starting at -1, I no longer see these x values. What's the range of this function? Yeah.
-1 to infinity.
-1 on to infinity. Oh, yeah, sorry, I interrupted you. That's what you said now? Okay. Cool. The next function, which is intended to have some controversy, though. Take a stare at that.
Are there supposed to be arrows on the end also?
Let's put the arrows on it. So by looking at this graph, tell me, what is the domain? Is anything not in the domain? No, so I guess it's all real numbers, however it is that you want to write that. So I'll write it 3 different ways. All real numbers. You could write it -infinity to infinity. So I don't think the textbook does this, but there's a standard symbol that mathematicians use to denote the set of all real numbers. And that's R, but in a blackboard bold font. So if you use that, I'll know what you mean. What's the range? What is the range of this function? Yeah. negative 2 to 2. And this is where the controversy is. Inclusive or exclusive? You said inclusive, right? How many people would want to say inclusive? How many people would want to say exclusive? How many people would want to say, well, it's really hard to tell just by this finite resolution graph, isn't it? Yeah, so maybe that's the best answer. I happen to know, well, I don't remember what formula I went down to give this, but I do remember it doesn't actually achieve the values of plus or minus 2. So I happen to know that it should be exclusive. But it's hard to tell that from the graph sometimes. If I gave you this problem from that picture, asked you for the range, and you told me negative 2 to 2 inclusive, I would be okay with that answer. People feel pretty good? Nice. So let's close by just remembering graphs are a very useful way of encoding information, possibly from real-world things. So a population of bacteria, which grows following an exponential growth model, if you plot that population in terms of time, is predicted by this model. Population is in millions of cells, time is measured in hours. By looking at this graph, can you read off what the population is when the experiment begins at time 0? What's the population? 1 million. What is the population after 2 hours? 2.5 million. Or maybe, if you happen to like scientific notation, 2.5 times 10 to the 6th. Which does have a very real advantage. If someone says 2.5 million and 2.5 billion, unless you like listen really carefully, those sound the same, but they're very much different. Scientific notation, you can definitely tell that they're different. And it doesn't take up any more space to write. Cool, so the payoff is just remember, you can always read off information from graphs, and that's particularly relevant if this graph happens to measure something that you're interested in. So with that, I think I'm about at my stopping point. There's one topic which I didn't get to, which we will hit next time, and this is the idea of graphing piecewise functions. With the payoff being, if you can graph every piece of a piecewise function, then you can graph that piecewise function. And we will start with this on Monday.